G'day there. This is a video exploring why subduction of the oceanic crust underneath the continental crust is just not possible. And when you look at what needs to happen for it to be true, I think you'll agree that it just can't be possible. Can't be true. This is a graphic from the Wikipedia. Wikipedia entry on subduction has this graphic here. If you click on that, you'll be viewing what I'm viewing. Now, I understand the graphic is indicative and isn't perhaps scientific description at all, but essentially it gives the details that I need. It's saying that it's saying here 500 degrees, 1000 degrees Celsius. Right, for that rock to bend, it has to become malleable. If you hit a rock with a hammer, it doesn't, it just crushes up. It doesn't. If you get a sledgehammer and hit a rock, it just breaks up. Unlike, say, for example, gold, which is malleable. If you hit that with a hammer, you can flatten it out into a sheet. Rock does not have that property. Okay, so if we go to the Wikipedia entry on lava, okay, so we've got lava here is a liquid at temperatures from 700 degrees to 1200 degrees. So this is what liquid rock looks like, and that is what, in this graphic is being proposed, is that the rock turns into a liquid. We have, either it's a solid or it's a liquid. It can't be a state in between. So, what they're suggesting is that at some point the rock, for it to bend, must its temperature must be between 500 and 1000 degrees Celsius. All right. So what I've got here is, I'll just turn a couple of layers off. What we've got here is a model of the Earth, and it's a cross section through the equator, and 1 millimeter represents a kilometer. Okay, so we've got the inner core here, we've got the outer core here, and we've got the mantle, the third layer. And if we zoom in, we've got the asthenosphere being shown in this region here, and then we've got in green we've got the continental crust, and in yellow we've got oceanic crust, which is the lithosphere. Okay, so the oceanic crust and the continental crust represent the lithosphere, and the area beneath it is the asthenosphere. Now, if we go to the Wikipedia entry on asthenosphere, we read here, the lithosphere and asthenosphere boundary is conventionally taken at 1300 degrees Celsius. Okay, so on our model, this area here is molten rock. It's 1300 degrees. Okay, so once again, lava is a liquid at temperatures from 700 degrees to 1200 degrees. Okay, so rest assured this area here is molten rock. Alright, so just exploring further what area we're looking at. We'll just zero that. If we go to South America, okay, this is the area that I'm looking at. Just turn on the equator grid. Okay, so we've got the equator going through here. So we've got continental crust being shown in billions of years, and oceanic crust being shown in millions of years. Now, I'm a creationist, and I do not believe in millions and billions of years. I believe that the Earth is a little bit over 6,000 years old. And what I do acknowledge is that there's a difference between the age of the oceanic crust and the continental crust. Because the dating method is based on the decay of the rock. So what I do acknowledge is that the continental crust has decayed more than the oceanic crust. and that is indicative of age, but not millions and billions of years. Okay, so we turn off the layer and we zoom in to this point here, and we'll just straighten it up, and we'll turn off the grid layer. So we've got a mountain range here, which is the Andes, then we have a shallow point here, and then we have submerged continental crust, and then the Atacama Trench, which extends to down the west coast of South America. And we'll just go to another map, this map here, which shows the heights of the oceanic, the sea floor, shown to the left of 0, which is sea level, through this region here. So that shows the heights of the sea floor, and to the right of sea level we're showing the heights of land masses. So if we zoom in on South America with this line here, which is the equator, and what I'm showing in my model is this mountain range here. We've got a low-lying region, submerged continental crust, and then the Atacama Trench. Alright, so we'll go to our model and we see the mountain range, which is about 4 millimeters high in the model, and that represents 4 kilometers or 4,000 meters. We've got the shallow section through here. We've got the submerged continental crust being shown in this area here, and then we've got the 8 kilometers deep, 8,000 meters deep Atacama Trench being shown here. Alright, so what people who believe in subduction have to believe is, we'll just turn on the subduction layer. Alright, this is at 25 degrees. We'll just go to the Wikipedia entry on the on subduction, and we've got the slab sinks at an angle of approximately 25 to 45 degrees to the Earth's surface. Okay, so we've got this at 25 degrees, this subduction layer, and we'll just turn on the 45 degrees layer, and there we go. So this is being shown at 45 degrees. So people who believe in subduction have to believe that the rock at this point here suddenly becomes malleable. And there's 2 reasons that you might say it's becoming malleable: because of the asthenosphere, the contact with the asthenosphere. But why does it not become malleable out here where it's in contact? So that can't be a reason for it becoming malleable just because it's in contact with the asthenosphere. So then you might say, well, it's because the oceanic crust and the continental crust are pushing up against each other, and that's why the oceanic crust is pushing up against the continental crust, and that's why it becomes malleable. But that's not the case, because with subduction it goes under. It's not butting up against each other, it's slipping under. So there's no real pressure created at that point in terms of high pressure, so therefore the temperature wouldn't increase. So for the rock to turn from a solid into something that's malleable, what's causing that to happen? In expanding Earth model, the oceanic crust is simply pushing up against the continental crust, and that's all that's happening. With subduction, if it's becoming malleable underneath, what's causing it to become malleable at the top? What's causing it to become malleable here? There's nothing causing it to become malleable, and either it's the temperature of the rock is such that it's a solid. If it becomes a liquid, then it's malleable, yes, but it's not going to continue out through this region here or through this region here. If it becomes malleable, it's just going to re-enter the asthenosphere at this point here. There's no reason to think that if the rock becomes malleable, so it becomes a temperature, as we saw with the lava entry, The lava is a liquid at temperatures from 700 degrees to 1200 degrees. Okay, so the rock is no longer a solid, it's a liquid. So it's not going to continue out through this section here. For it to be able to bend, for rock to be able to bend, it has to become a liquid. Right? And if it becomes a liquid, then it's not going to continue out through this section here or this section here. Subduction is a lie. It's a fabrication. It's not true. It can't possibly be true. If you think about it, for this rock to become malleable, for the what's causing the upper part of the oceanic crust at this point here to become soft, right? There's no reason why at all. Oceanic crust just does not become malleable all of a sudden. If the contact with the asthenosphere is the reason, as I've said, then why don't we see a thinning of the oceanic crust throughout this region here, where the asthenosphere is in contact with the oceanic crust? There is no reason for the oceanic crust to suddenly bend and go down into these regions here. Once again, if it becomes a liquid at this point here, then it's not going to be able to extend out into these regions and cause any sort of impact on this mountain range. Okay, so I think I've covered everything I wanted to say. Subduction just is not possible. It defies basic properties of materials. To sum up, either this rock is a solid or it's a liquid. If it's a liquid, then it's not going to continue at this angle or this angle. It's just going to simply re-enter the asthenosphere. If it's re-entering the asthenosphere, why? How did it become a liquid? If it's because it's in contact with the asthenosphere, then you would see a thinning of the oceanic crust, and these things are not observed. So subduction is not observable. It's not occurring. It's just I can't believe people believe in it. It's just utter rubbish. All right, thanks for listening, and God bless.